Hello, welcome to this video on Chateliers Principle. This video is all to do with reversible reactions and equilibrium. In this video, we are going to look at some of the features of reversible reactions and systems at equilibrium, and we are going to pay particular attention to what this bloke said. This is Henri Louis Le Chatelier, and he had some really important things to tell us about how reversible reactions happen and what we can do with them when they reach equilibrium. Now, it would be really helpful if you already know some key things before starting this tutorial. These include energy changes, so you should remember some things about endothermic reactions and exothermic reactions. It would also be really useful to know about rate of reaction, so a little bit about collision theory, how reactions take place, and how we can speed them up by heating them up, increasing concentration, pressure, surface area, or using a catalyst. You should have some idea of what a reversible reaction is, and you should understand what I mean by the term equilibrium or dynamic equilibrium. Now, if there's anything here that you don't already know and you're not confident with, it would be a good idea now to pause this video, find out a little bit more about these things, and then come back when you are ready. Okay, so first we're going to look at energy changes in a reversible reaction. So here we've got standard reversible reaction. We've got some reactants that we're starting with, some products that we are making, and usually the reaction would go in the forwards direction only. But because this is a reversible reaction, this reaction can also go backwards. So the reactants turn into products as usual, but the products can also turn into reactants as well. So one thing that's really important to know about is the energy change in a reversible reaction. So when the reaction goes forwards, it's either endothermic or exothermic. So it either absorbs a certain amount of energy to go forwards, or it releases energy. So it doesn't really matter what it is. What's important is that the other direction is the opposite. So let's assume that the forward reaction in this case is exothermic. It gives out heat energy. It releases heat energy to the surroundings. And in this case, let's just choose a number. We're going to say that it releases 2,187 kilojoules per mole. So 2,187 kilojoules of energy are released every time a mole or a certain amount of reactants is reacted to make a product. That's how much energy is released. So what you need to understand is that when the reaction goes backwards, it will no longer be exothermic. In the reverse reaction, it will be endothermic. This means that when the reaction goes backwards and the products turn back into reactants, heat energy is absorbed or taken in from the surroundings, and it is the same amount. So if we're going backwards and we're going from products to reactants, then 2,187 kilojoules of energy will be absorbed per mole. So don't worry if you haven't come across moles yet, it just means per amount of stuff. So if you use a little bit of energy will be given out. If you use loads of reactants or products, then loads of energy will be given out. So you have to have it per mole or per amount of substance to make it comparable. So two features here that are really important. One, that the energy change in a forward reaction is the opposite to the energy change in the reverse reaction. And secondly, that the value of the energy released or absorbed is the same whether you're going forwards or backwards. It's just that in one direction it's released and in the other direction it's absorbed. And this could be the other way around, so it could actually be the forward reaction that's endothermic and the reverse reaction is exothermic. That's fine. How you would know this in an exam, if it didn't explicitly tell you that the forward reaction is exothermic, it might give you a value. So we would have the equation for the reaction here, and sometimes at the end we have delta H, so that's Greek capital letter delta, equals, and then we have a number. And that number will tell you if it's exothermic or endothermic. In an exothermic reaction, delta H is negative. So if there's a minus sign here, it tells you that it's exothermic. And in an endothermic reaction, delta H would be positive. So that's one way of figuring out whether you've got an endothermic or an exothermic reaction. And if you've got a reaction where you have the reversible reaction symbol, arrow, like that, and delta H, the energy change, is written at the end, it always refers to in the forwards direction. So if If delta H is negative, then the forward reaction is exothermic. If delta H is positive, then the forward reaction is endothermic. Okay, so the stuff that I've written in red and blue is the stuff that I need you to know. The stuff that I've written in black is some tips to help you in an exam if you're not sure whether you're looking at an endothermic or an exothermic forward direction reaction. Now, at this stage in the video, I want to introduce you to a really important idea. Many chemical reactions that are used in industry, in factories and things like that, to make products and to make money for business, many of those are reversible reactions. So, let's put ourselves in the position that we are a business owner who owns a chemical company, and we use a reversible reaction to make a product that we want to sell. So we are really, really interested in this chemical here. And we buy in loads of reactants and we react them together and we make our product, we can sell it and we can make loads of money. You should be able to see that there is a problem for a business owner, chemical industry business owner, if you're using a reversible reaction, if you're trying to make as much money as you can. And that is that if you're using reactants and you're making products, that's great, but some of those products will be breaking back down or reacting together to form the reactants again. So you don't get all of the products out that you would if it was a straightforward, irreversible reaction. So what we want to do is try and maximise how much product we can possibly make from this reaction. Now, looking at the information that I've written onto this slide, there are things you can do with temperature that would mean you would make more product. So, in terms of temperature, you could either heat this reaction up, and that would push it in one direction, or you could cool it down, and that would push it in the other direction. So I want you to pause the video now, have a little think. Would you heat this reaction up if you wanted to make more products, or would you cool it down? If you said that you would cool it down, well done. Because what we can see here is to go in the forwards direction, heat needs to be removed. It needs to go out to the surroundings. So if you cool it down, then you're pushing it in this direction. That would favour that direction. If you heat it up, well, the endothermic needs you to heat it up. So the reverse reaction requires you to provide some heat energy. So if you heat it up, it will favour the endothermic reaction and it will push it back to reactants again. Okay, we're going to look at this in a little bit more detail because we're going to look at Le Chatelier and what he says. But it's all to do with this idea that we can make more products or we can make more reactants by changing the conditions in the reaction. So I'm going to leave you here with this last little idea that if you want to go in the forward direction, which is exothermic, then you should cool it down and that will push it that way. If you want it to go in the reverse direction, in the endothermic direction, then you should heat it up, okay? So if you want it to go in the exothermic direction, cool it down, whether that's forwards or backwards, and if you want it to go in the endothermic direction, whether that's forwards or backwards, heat it up. And we will return to this idea in a moment. So let's return to this idea of equilibrium. You should already have an idea of what dynamic equilibrium means, but just to remind you, we have got a reversible reaction taking place. The reactants are turning into products. So on my graph, if I show you how much reactants we've got over time, so I'm just going to colour code this to make it a little bit easier to see. The reactants, well, at the beginning of a reaction, you start with loads of reactants, don't you? And then over time, we end up with some products. So our reactants, the amount of reactants we've got, that goes down over time, okay? So we start with loads of reactants, and over time, that drops down, drops down, drops down, and then it stops. Now, what you can see here is that I haven't gone all the way down to the bottom because this isn't a straightforward reaction. This is a reverse reaction, which means that eventually the products start turning back into reactants. So we do keep some reactants in our beaker or flask or wherever this is taking place. So let's have a look at what happens to products over time then. Your products, well, you start with none because we're starting with reactants. So you haven't got any products to begin with. And then your reactants react. You start making products really, really fast. And you should recognise this from rate of reaction. It starts to drift off like that. Okay? And what you should remember from rate of reaction is that you're starting very quickly, you're making lots of product very quickly because there are a lot of collisions happening because there's loads of reactants. We've got loads of reactants. They collide, and we start making product very fast. Over time this slows down because we're running out of reactants now, and your amount of product eventually levels off, which means you're not making any more, so the reaction stops. So in a reversible reaction, where you've got both of these lines on the graph, where both of them go flat, that's where in a normal reaction you would say the reaction stops, but in this sort of reaction, this is where it hits what we call equilibrium. Because after this point in time, we have no change to the amount of reactants and we have no change to the amount of products. They stay as they are. They're not the same as each other. You can see we've got loads of products, we've got a little bit of reactants, but they're not changing over time. So it looks like the reaction stopped, but it hasn't. The reactants are still turning into products and the products are still turning into reactants. But what's important to make something a dynamic equilibrium is that even though both of those reactions are happening, they are happening at the same rate. So the forward and reverse or backward reactions happen at the same rate. That word's really important. They are as fast as each other. So although your reactants are turning into products, just as fast your products are turning back into reactants, so we don't see any overall change. And just because this is a recap of equilibrium, there is another condition for a system to be at equilibrium, and that is that it has to be a closed system. So this has to be taking place where matter can't get in or out, so like a sealed flask. So there we go, there's our meaning of dynamic equilibrium. And if you've got a reversible reaction, at some point it will reach this point here where the concentrations stop changing, and this is called dynamic equilibrium, or just equilibrium for short. So now I want to introduce this bloke. This is Henri Louis Le Chatelier, and he has important things to say about a reaction that is at equilibrium. So it looks like nothing's changing, but the reaction's still going. It's just that the forward and the reverse reactions are happening at the same rate. And what he said is if a change is made to the conditions of the reaction when it's at equilibrium, then the system will respond to counteract the change. And what that means in practice is that if you've got a system at equilibrium, you've got a closed flask, it looks like nothing's happening, but you know it is because you know there's a forward and a reverse reaction happening at the same rate. If you make some sort of change to the conditions, so you could heat it up, you could cool it down, there's other things you could do as well, then the system will respond to try and cancel out what you've done. So this takes us back to this idea of endothermic in one direction and exothermic in the other. And it tells us why, if you heat it up, it will go one way, and if you cool it down, it will go the other way, because you're putting a change in place by heating it up or cooling it down. And the system responds by either making more reactant or more product, which counteracts the change in temperature that you have put onto the system. Okay, so this phrase here in the speech bubble is known as Le Chatelier's Principle. This is his idea, and it tells us a lot about what happens to reversible reactions when they're at equilibrium, and how, really importantly, we can affect equilibrium to make us more money if we work in the chemical industry. What changes to conditions we could make that will make us more product and eventually more money. So let's go back to this energy changes in reversible reactions. Okay, so in this example, I've swapped them around just to remind you that the forward reaction can be endo or exo, and the reverse reaction will always be the opposite. So in this case, our forward reaction is now endothermic. It's absorbing heat from the environment for the reaction to take place in the forwards direction. When the backward reaction takes place and the products turn into reactants, heat energy is released. That makes the reverse process exothermic. And remember, the number's the same as well, so if the forward process is taken in 5,000 kilojoules per mole, then this one is given out 5,000 kilojoules per mole. The number stays the same as well. So, Le Chatelier says that if this reaction is at equilibrium, so we've made all the product that we're going to make, it's sitting stable. If you remember our graph, so from earlier on, then our concentration of reactants has gone down to here, that's fine. Our amount of products has gone up, but only to here, and it's not changing now. We're not making any more products, so we can't make more money. So what we really want to do is impose a change on this system so that when the reaction responds, it gives us more product. So we want to push this up here, okay? And if we're making more product, that means we'll end up with even less reactant. So what we're trying to do is spread that out even more. Okay, so let's impose a change on this system. Let's say the reaction's taking place in a flask and we heat it up. So we provide some heat energy, okay? So we're heating it up. How will the reaction respond? Well, Le Chatelier says that it will respond to counteract the change. If you make it hotter, the reaction will go, I don't want to be hotter, so it's going to make it colder to cancel out the change. So you make the reaction hotter. Which direction is going to make the reaction colder again? Try and remember which one feels colder. Pause the video now, have a little think. So if you go in the endothermic direction, then the heat energy you put in gets absorbed by the reaction and the whole thing cools back down again. Endothermic reactions feel cold because the energy is absorbed into the chemicals, so you can't feel it anymore. So heat it up, it will push it in the forwards direction. Okay? Now what we say is that if you heat the reaction up, the language we use is that equilibrium shifts to the right. Which means if you've got a certain amount of reactants and a certain amount of products, let's say we're at equilibrium, let's put us here, so we've got more reactants than products. Equilibrium shifts to the right, we end up down here, we've now got more products than reactants. Okay? Or we could be bang in the middle, we could have equal amounts of each. Equilibrium shifts to the right because you've heated it up, again you make more product. So the language is equilibrium shifts to the left or to the right. If it shifts to the left, it means you're making more of this. And if it shifts to the right, it means you're making more of that. Okay? So what else could we do? If we're heating this reaction up, that shifts equilibrium to the right. We make more product. That's great. If we're in business, we want to sell the product, let's heat it up. But there are other things you could do as well. You don't just have to change the temperature. So other things you could change about this reaction include concentration. So let's have a look at changing concentration. And remember, concentration is all about the number of particles you've got. So if something is highly concentrated, you've got loads and loads of particles in there. And if something's not very concentrated or it's more dilute, then you don't have so many particles in there. Okay, so here's some particles. Let's have a little play around with what happens when we change this. So let's put our reversible reaction in. So this reaction is at equilibrium, and now we're going to change the concentration. So let's increase the concentration of reactants. Let's put more reactants in. Okay, so there we go. We've put some more reactants in. But the reaction, because you've changed the conditions, the reaction needs to respond to counteract what you've done. So you put more reactant in, the reaction goes, but I didn't want more reactant. So I'm going to turn that reactant into product. So the reactant that you put in, the extra stuff, gets changed into product. Okay, so overall, what have we done? We increased the concentration of reactant, but the reaction has responded by turning it into product to counteract the change that we put in place. So is this good for business? Is this bad for business? In this case, increasing the concentration of your reactants is great because it forces the reaction to form more products. More products means we can sell more, means we can make more money. Which way is equilibrium shifted? Has it shifted from the left to the left, or has it shifted to the right? In this case, equilibrium has shifted to the right because it means we're making more product. That's what's been done overall. That's the result of what we have done. Okay, so now we have a new position of equilibrium where we've got more product and less reactant. Our original position of equilibrium, if you remember, had 4 reactants and 4 products, so it was bang in the middle. This new one is still equilibrium. We've still got the forward reaction and the reverse reaction happening at the same rate in a closed system. This 4 isn't changing. This 6 isn't changing. They're staying constant, so it's still equilibrium, but it's a new position of equilibrium further to the right than it was before. So let's put more reactant in because we're greedy businessmen. We want to make even more money. So here we go. We pile in loads more reactant, and again, some of that reactant go off and it will become product again. There we go. And again, equilibrium has been forced to shift to the right, so we're making more product. What else could you do with concentration? You don't have to increase concentration, you could decrease concentration. So what if we just take away some of the reactant? What would happen then? Pause the video, have a think. If we remove some of our reactant, take it away, what's going to happen then? Well, we remove some reactant, the reaction is, well, I was balanced before, I was stable, I was at equilibrium, and you've changed it, so I'm going to fix that. You've taken reactant away, I'm going to put more reactant back. And the only way the reaction can do that is by taking some product and turning your product into reactant. And it puts it back, okay? So now we've got a different equilibrium again, because now we've got 5 particles on the left. Obviously this represents lots more, because you have millions of particles in a reaction. But we've got 5 on this side and we've got 6 on this side, which we've not seen before. But this is still equilibrium. It's settled back out to find a new position where the reactants and the products don't change. They're constant. They're not equal, so we don't have the same amount on each side, and that's fine. But as long as they're not changing, then it's now at equilibrium again. So in this case, equilibrium has been shifted to the left, because when we removed some of our reactant, the reaction responded by turning some product back into reactant. We made more reactant overall, so equilibrium is shifted to the left. That one's not so good for business. Now, just before I move on to the last way that you can affect a position of equilibrium, just to point out, I have been changing the concentration of the reactant. I increased it again, I decreased it. Just to note, you can also change the concentration of product. So if you're making product and you start to take it away and bottle it as soon as you're making it, then you're reducing the concentration of product. If you take the concentration of product down, the reaction responds by going, oh, well, I'm going to put that back. So the reaction gives more reactants and turns them into product. So equilibrium shifts to the right. So we don't just need to worry about concentration of the reactant. You can also think about what you could do with concentration of product as well. But that's a second way that you can affect the position of equilibrium. We're going to look at a third one now. Okay, and the third one is to do with working with gases. And what we can change, a condition that we could change if we're working with gases, is pressure. And if you think back to your rate of reaction topic, pressure is all to do with how many particles you've got in a set amount of space, in a set volume. So if you put more gas particles in the same volume, you increase the pressure because those particles are pushing on the walls of the container. So I'm going to draw some particles again. I will keep them in a container, in a set volume, so that you can see what space we've got. So here's our volume, our container for the reaction. In this case, I'm going to give you a real reaction for this one that you're going to come across in the next tutorial, because it's easier to see where I'm coming from. So we're going to look at a process called the Haber process, where we take nitrogen and hydrogen, react them together to make ammonia. Now this reaction needs balancing, so we need to make sure we've got the same number of nitrogens on the left as on the right, and the same with the hydrogens. So there's our reaction. So our reactants, in this case, are going to be nitrogen and hydrogen. So we'll highlight those so that you can see them. They're going to be our reactants. And our product is going to be ammonia, NH3. Don't worry about what it's called for now, but they're our reactants and they're our products. So I'll draw some particles in our volume, in our container, so that you can see what we've got. Okay, so to keep things simple, I'm still keeping them just all in one circle. So I've not drawn out the 2 nitrogen atoms stuck together, or the 4 atoms involved here. I'm just going to keep them in a circle so that each circle is a molecule. So this is a molecule of nitrogen made up of 2 nitrogens stuck together. This is a molecule of ammonia made out of a nitrogen and 3 hydrogens stuck together. So the reaction tells us, this is why I've used a real reaction, that to get this reaction to balance, we need 1 nitrogen molecule reacting with 3 hydrogen molecules, making 2 ammonia molecules. And I've represented that accurately here with the number of molecules that I've got. Underneath, I'm just going to write down what we've got as well so that we can keep track. So let's not worry too much about how many atoms are in each of these. Let's just look at the molecules as a whole, which is why I've kept them as a circle each. The reactant's made up of 4 molecules, 1 nitrogen and 3 hydrogens. 4 molecules. The products are 2 molecules, okay? So if we move this reaction to the right, if we go in the forward direction, then these 4 molecules become 2 molecules. And if we go in the backwards direction, then these 2 molecules can become 4 molecules. So we are looking at what happens when we put pressure in place when we make changes to the pressure. So there's a certain pressure inside this container at the moment with the number of molecules we've got. So let's increase the pressure, and to do that what we have to do is make that volume smaller. Okay, so what I've done now is I've squashed the same number of particles, those same 4 reactants and 2 products, into a smaller volume. I've made that volume smaller. So these particles are all bashing into each other because they're all gases. They're bouncing around and hitting the walls. The pressure is much higher. So this is an increased pressure now from before. Now we've made a change to the system, and Le Chatelier says that when you change conditions of a system at equilibrium, the reaction will respond to counteract what you've done. So you've put them under increased pressure. So what does the reaction want to do? The reaction wants to decrease the pressure again. Okay? Now the reaction can't change the size of the volume that it's happening in. That's for us to decide. So we change the size of the container. It can't do anything about the size of the container, but what it can do is turn reactants into products or products into reactants. So which way would relieve the pressure again? Would you want to turn these 4 molecules into just 2? Or would you like to turn these 2 into 4? Pause the video, have a think through what I've said. So would we turn these 4 into these 2? Or would you turn these 2 into these 4 to relieve the pressure on the system? Well, in order to decrease the pressure, we need to free up some space inside this container. And the only way we're going to free up some space, give these particles more room to move about, is if we turn lots of particles into fewer particles. If we go forwards, then we turn 4 molecules into 2 molecules. If we go backwards, then we turn 2 molecules into 4 molecules. So we want to make some space, we want to get rid of some molecules, so what we're going to do is we're going to turn the 4 reactants into products. Okay, so let's take these 4 reactants, the nitrogen and the 3 hydrogens, react them and turn them into some ammonia. There we go, reaction's taken place, and you can see hopefully now that there's loads more space in that box now for these particles to move around. So the reaction has responded to you increasing the pressure, and it's decreased the pressure again inside the box by changing the reactants into products. Now I'm only picking out a few molecules out of this reaction. If this was happening in a conical flask, there'd be millions of reactants. So although now it does look like we've just got product, obviously we've got other reactants and products in there as well. So we've still got nitrogen, we've still got hydrogen, we've still got ammonia. We're just looking at a set few molecules. And hopefully now you can see that equilibrium has shifted in a certain direction. Has it shifted from left to right or from right to left? Equilibrium has shifted to the right, because now, as a result of us increasing the pressure, the reaction has responded, it's made more product, it's made more of this, so it's shifted to the right. And now we're at a new position of equilibrium. Remember that there are other nitrogen, hydrogen and ammonia involved as well. We're just looking at some of them in particular. So if we increase pressure, equilibrium shifts to the right. And if this is us in industry, we want to make loads of ammonia and sell it because we're in business, then it's probably a good idea to increase the pressure in terms of the amount of ammonia that we're going to make, okay? We call it the yield. The amount of stuff that we make that we can sell is called the yield. So we want to increase the yield of ammonia, then increasing pressure is a great way to do it, because we go from having 4 molecules of reactant to 2 molecules of product to counteract the change that we've put in place. So there's your third way of changing the position of equilibrium and finding a new position of equilibrium where we're making more products. Similar to concentration, remember you don't just have to increase pressure, you could decrease it, you could make this area much larger. And if that's the case, if you put all these particles in a much larger area, well then some of those ammonia are going to turn into nitrogen and hydrogen to fill up the excess space that you've provided. Okay, so we're nearly finished. Last couple of slides. Just want you to notice something. The 3 ways of changing the position of equilibrium that I've talked through are temperature, increase or decrease it, increasing or decreasing concentration, and increasing or decreasing pressure. Do they look familiar? They should look familiar. Changing the temperature, changing the concentration, and changing the pressure you have seen when you've looked at how to speed up a reaction. So how to change the rate. Now be careful, because we're not changing rate here, we are changing the position of equilibrium. And it's very important that you know what your exam questions are asking you. So if you're looking at changes to temperature, changes to concentration, or changes to pressure, make sure you know, are you trying to make the reaction go faster or slower and affect the rate? Or are you trying to push a reaction forwards or backwards and affect the position of equilibrium? Because they're two different things. But temperature, concentration and pressure affect both different things, rate and position of equilibrium. And if that's the case, if we've got temperature, concentration and pressure, then what about catalysts? Catalysts are slightly different. Catalysts, you should know, speed up the rate of a reaction without being used up themselves, because they provide a different route for the reaction to take with a lower activation energy. So let's go back to our graph of how much reactants and products we've got. So here we've got, over time, as we go from left to right, we've got concentrations of these various chemicals changing over time. And the red one is the reactants, and the blue one is the products. So again, we can see reactants, we start with loads of them, they get used up. Products, we don't have any, and then we make some. And eventually we hit a point where the amount of product and the amount of reaction stops changing and the lines go flat, and this position we call equilibrium. Doesn't mean the reaction stopped, it means it's still going, but at the same rate in the forward and backwards direction. Now what happens when you throw a catalyst in? Well, we know they speed up reactions, so they would speed up the rate of a chemical reaction, but they speed up the forward reaction and they speed up the backward reaction by the same amount. So the reaction is faster, which means you will reach equilibrium sooner, but it doesn't actually change your position of equilibrium. It doesn't make more product or make more reactant, because it has the same effect on the forward and the backward reaction. So I'll show you quickly how this graph would change if you threw a catalyst in. So the reactants would be used up faster, so it'd be steeper, and the products would be made faster, so it'd be steeper, like that. Okay, and you can see on our new graph that they're starting to go flat here now. So this is our new equilibrium time, so this is how long it takes to get to equilibrium, but the equilibrium is still the same as it was before. So we haven't made more products, we haven't made more reactants. We're still ending up overall with the same amount of product that we had before and the same amount of reactant that we had before. They're level. Okay, so it just means that we reach equilibrium sooner. It's all to do with the time. So it's still useful if you're in business, throw a catalyst in. You'll get to your position of equilibrium sooner, and then you can start playing with temperature, concentration and pressure to get yourself some more product. So catalysts do not affect the position of equilibrium. They just help you reach it sooner. So that video explains all about the Chateliers Principle, what he said, and what it means for the position of equilibrium. Remember the language shifts to the left and shifts to the right is what you should be using in your exam. And make sure that you're aware that the three things that can affect the position of equilibrium can also affect the rate. So you need to be very careful and look at what the question's asking you.